I hope you can see that there is some light coming through. Also assuming that these lenses are not damaged. And if we put another one on there, well, that blocks it out completely. A little bit of light's coming through there. Actually, let's kill the lights and just, I think you'll be able to see it better. Do I need to pull it back, or is this good enough?
I need to pull it back because there's a glare. Or is it?
That's better. Can everyone see?
Yeah.
Other than the fact I'm standing in your way? All right, so you can see some light is coming through. It's not completely black. Now it is completely black.
Oh, there's still some light.
Still some? Okay.
Very little.
Well, if I rotate this,
Oh, wait, one.
definitely see light coming in through there.
I said, there you go, you had it.
Yeah, there it is.
All right.
That's one.
So that should be perpendicular to whatever the top lens is. And in fact, it is. Polarization of light. Any questions? All right. Now what do I want you to know from chapter 38?
So we going ahead and going into chapter 38?
Yeah. This is probably, it's one of my favorite chapters.
Because it's the last one, or?
No, because it basically is saying that everything you've learned up till now is a little bit off. Someone once described education as, when you first start out, they teach you what, then they teach you what and how, and then they teach you what, how, and why, and then they teach you to question everything you've ever learned. This is the, let me teach you to question everything you've ever learned. All right, so let's drop back to Maxwell. When I outlined it briefly, electromagnetic wave, he came up with the fact that the speed of light, C for the speed of light, is equal to 1 over the square root of mu sub naught, epsilon sub naught. Now mu sub naught and epsilon sub naught are constants. Mu sub naught is equal to 4 pi times 10 to the negative 7th Tesla meters per ampere.
That's a lot of words.
Yeah. Tesla is the standard, international standard unit for magnetic field.
Oh, it's a car.
Tesla was
Named after the same person.
He's the one that invented X-rays.
I think that was Röntgen. Thank you.
No, he was the
Tesla
father. Was the father of X-rays.
Tesla was, he made AC currents.
Hmm?
He's the one who made it possible,
Yeah.
or made it viable. He's the one that Westinghouse exploited.
Yeah.
Oh, yeah, he was the one that got screwed with by Thomas Edison.
Yeah.
Dipendently. All right,
That is 4 pi, correct?
that is 4 pi, yes. Epsilon, so this is known as the permeability. I know there's a dark marker around here somewhere.
I got a Sharpie.
I'm trying to avoid the Sharpies for now, but I might come back to you on that one. This is the permeability of free space. Basically, it's how space reacts when in the presence of a magnetic field, what happens. So that's what this number tells us. Permeability of certain metals around here make things more magnetic. Certain other objects, like copper, when you expose it to a magnetic field, it basically creates an anti-magnet to some extent. It repels, or it does not attract, does not increase the magnetic power. And there are other metals like aluminum, which when exposed to a magnetic field will become magnetic temporarily, but when you take it away, the magnet away from it, or the magnetic field away from it, aluminum goes back to normal. So permeability deals with how space reacts, how the vacuum reacts to the magnetic field. Epsilon sub naught is equal to approximately 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. Coulomb is just the international unit for charge, and Newton for force and for distance. This is the permittivity. I wish they had come up with more distinct names, but permittivity of free space. And it basically tells how a material reacts in the presence of an electric field. So permeability, magnetic field, permittivity, electric field. So Maxwell derived this. It came out with a value of, well, actually, you tell me if you go through the calculation there, what is the speed of this electromagnetic wave? I guess historically, he found the speed of an electromagnetic wave.
$948,251. I might be off somewhere.
Something is off there.
What do you say? You said 948? Yeah, 948,251.
Something's still off. If you got a number that small, then either, I assume you took the square root.
Yep. Same thing again.
See, because if I multiply these together, just looking at the exponents here, I got 10 to the negative 7th times 10 to the negative 12, which is 10 to the negative 19th. The square root would put it somewhere around 10 to the 9th. It ultimately, with the other factors, or 10 to the negative 9th, then the reciprocal makes it 10 to the 9th.
Oh,
Back it up.
When I times them together, I get 1.112 to the 10 to the negative 12.
Yeah, that's not right. Let me see what you're typing into your calculator.
I got 1.05 to the negative 10 to the negative 6.
It's, 4 pi times 10 to the negative 7th. That's a 7.
That's a 7?
Oh,
That's a 7.
Okay.
yeah, that would cause some problems.
I thought that was a 2.
Yep.
thought that
Oh, I
was
was
two.
with you on it.
I knew it was.
Alright, that might change the answer a little bit though.
Okay, yeah, I hope so.
It's a. Let me try to map this.
Is it negative stuff?
So 299 million,
There we go.
Okay.
Yeah, 299 million.
863,380.5.
Now, it's a little bit off from the speed of light because, well,
It's,
this number here is rounded.
And also, that's faster than the speed of light.
Barely. Speed of light is 299 something.
299, 792, 458.
Okay. Yeah, this number right here is rounded. Now, Maxwell comes out with this and he says, this seems too much of a coincidence. And he speculates that light is an electromagnetic wave. And he's right on that. Physicists saw this have I done this part with you before?
I don't think so.
Well, it'll be quick if you remember it. Physicists look at that and say, this is remarkable work, but there's a mistake.
Yes,
I did do that. What was the mistake?
I don't remember. But I did write it down.
Or what was the believed mistake? There actually is not a mistake.
There's something about a constant in there, ain't there?
That's not the,
I don't know. When they add a constant number to it, or might be thinking of something else.
I could think of something else, I think we'll agree with that. Well, I'll save you some of the pain there, John.
Okay.
How fast are you moving right now?
Fast.
How do you come upon that?
Cause the earth is spinning, so we're moving.
Yeah.
So if the policeman pulls you
9.8.
over for going several thousand miles per hour, you're gonna go, yeah, that's fair.
Oh, no, here it is.
What you got there, John?
What we did, how you explained that there's like 5 different equations that have been added on to this.
Oh, yeah, well, yeah, I skipped over the Maxwell's equations, went straight to
Yeah.
this one. So, okay. So what's missing is relative to what? This is what the physicists believe. 30 years later, Einstein comes along and says, there's not a mistake. The speed of light is the same regardless of who's observing it. So, speed of light's coming at you and you're driving straight towards it. If you had a detector to measure how fast the light's coming at you,
It's the same.
it's speed of light. It's that number-ish. If you're going away from it, light's following you and you're traveling near the speed of light, but going away from it, when the light hits you, how fast is it going? The same. Regardless of how fast you're going, the speed of light is the same regardless. And this gets into implications.
So if you were going 99% the speed of light and you were seeing light, it would be just as fast as if you were standing still,
Yes.
even though you're relatively close.
Yes. And this has major implications. This was about 10 years, this comes out about 10 years after, I think it was a Harvard professor said, is the best physics students and said, get into engineering, we're almost wrapped up on physics. We just have a couple of little things that we're trying to figure out. And then in the next 20 years, it all changes. Not from an engineering point of view, but from a physics point of view, when you start getting into the relativity and then quantum.
Where will we be in another 20 years?
Yeah.
I think you just need the Harvard professor to go, hey, we're almost done here. So Einstein proposes a thought experiment. Got a mirror here on the ceiling, and down here, you've got a box that's gonna shine a light upwards. I'm gonna call this the lab frame. The box is moving off to the right at some speed v, and it's gonna shoot a light up. Now, because the box is moving, the light has a horizontal component to it, and so the light's gonna basically hit the mirror and then come back and hit the top of the box again. This distance here is h. So we look at the distance that the light travels. Think about a little triangle right there, got a right triangle. This distance from here to the halfway point is just, well, v times t divided by 2, it's just half of that distance. The height here is h, so that triangle, we have a height h and a base of 1/2 vt, and so my hypotenuse is h squared, square root of h squared plus 1/2 vt squared. So the total distance that the light travels is 2 times that, because it goes up and then down. H squared plus 1/2 vt squared, divided by time. So basically it's the distance divided by time, is the speed of light. All that's well and good. The other piece of it, if we look at the box frame, in other words, if you are in the box, what does life look like? Well, if you're in the box, you're not going anywhere. You got the mirror right here, the light goes up and comes back. So from the box's point of view, like boom, boom. From the box's point of view, the distance that the light travels is just 2 times h up and h back, divided by time. If the speed of light is the same, what has to be different?
Time?
Yes. This time and this time are not the same. The time in the moving frame is different than the time in the still frame. And we can derive this. Let's take it to the next step. Let's solve for h. So I have a little p down here. This is a t with a p subscript. It stands for proper time. I'll explain proper in a moment. So h is equal to 1/2 CTP. And now I'm going to take that and just plug it into that equation. Thank you. And I did something with the eraser. There it is. So what I have there is that I have C is equal to 2 times the square root of 1/2 CTP squared plus 1/2 VT squared divided by T. All I did was take our value that I got from H from the second equation, pop it into the first one. And now, just continue the math fun. I'm going to square everything in here. I got a 1/2 squared. I got a 1/2 squared. I can factor that out. Square root of 1/2 squared is 1/2, which is going to cancel out with that 2. So now I'm left with c squared, and then I'll square both sides, is equal to c squared tp squared plus v squared t squared divided by t squared. Ultimately, what I'm trying to get towards is what is the relationship between t and tp. So let's get rid of the fraction by cross multiplying, or multiplying both sides by t squared. So I get c squared t squared is equal to c squared tp squared plus v squared t squared.
I'm so happy that there's so many squares.
We'll do a square root in the end. We'll make
Do you
most of
have,
it go away.
do you hear how much I like it?
Bring this over. Now, at least everything is squared, not just some of it.
Yeah.
It's worse. So I got c squared t squared minus v squared t squared is equal to c squared tp squared. Now it's a matter of what form do we want the final answer in, and so that's the next bit I'm going to do. I'm going to get tp by itself, so I'm just going to divide by c. So I end up with t squared minus v squared over c squared times t squared equals tp squared. I'm going to factor t squared out on the left-hand side, so I get t squared 1 minus v squared over c squared is equal to tp squared.
Where do you get v squared over c squared from?
At this step right here, I divided everything by c squared. So the c squareds cancel here. Here I have v squared over c squared, and here the c squareds cancel out.
Okay.
Is that good enough?
Yeah, you're good.
We're almost there. Because there's a standard form. I'm going to divide both sides by this right here, bringing it over. Then I'm taking the square root, so I end up with t is equal to tp divided by the square root of 1 minus v squared over c squared. V squared, v over c shows up so much in relativity, they came up with a new symbol for it. It's the beta, this is the beta, and it just equals v over c. So if I have an object that's traveling at beta equals 0.9, that just means I'm traveling at 0.9 times the speed of light. So beta equals 0.9 means the speed is 90% the speed of light. I have basically the square root in the denominator, so this is 1 over the square root of 1 minus beta squared times dp. This shows up enough to give its own symbol, and that is a gamma. That's equal to 1 over the square root of 1 minus beta squared. And this is known as the Lorentz factor. Because Lorentz had done a lot of the math already by the time Einstein came along, but Lorentz refused to take that last step and accept the fact that the speed of light is constant regardless of the reference frame. So we are now left with our final form of time is equal to the proper time, actually, equal to gamma times the proper time. Let's think about the implication of this. If you're traveling at 90% the speed of light, so if beta is 0.9, what is gamma?
Well, wait a minute, what was so common that it needed to be gamma?
1 over the square root of 1 minus beta squared
Okay.
is common, and also V over C is common, so we got these two shorthand abbreviations.
3.16.
Something doesn't seem
Oh,
right
no,
there.
hang on, forgot the square.
So beta squared.
Yep. .294.
That sounded more familiar. All right, there are no units, it's just a number. It's a ratio of times. So you and your twin are here on Earth. Your twin gets on a rocket ship, goes to a distant planet, and comes back. And he's gone for a month. From his point of view. He's aged a month. The twin left back on Earth is aged almost 2.3 months. You're no longer the same age, even though that you're twins.
Oh, yeah, the time dilation.
Yep, and this is called time dilation. The faster you travel, the slower your clock is, biologically. If you drive 60 miles per hour to school,